Hi, you guys. I'm Matty Cartwright. I'm a first-year MBA student at MIT Sloan. And thank you guys so much for being at SSAC25, especially in this specific workshop. It's my pleasure to introduce the presentation, Don't Be a Square, Winning Super Bowl Squares with Data Science, presented by FanDuel. Please join me in welcoming our speakers, Keith Goldner, Vice President of Data Science at FanDuel, and Jason Feldman, Senior Manager of Pricing Strategy and Innovation at FanDuel, to the stage. Take it away, guys.
Thanks, everyone. So, as he alluded to, our talk today is going to be about Super Bowl squares and how we go about pricing up a market like that. So, I'm Jason. I'm on the sports modeling and innovation team, along with Keith, who will also be joining me throughout this talk. Our team's job as a whole is about working with our trading team to power the odds for all the different markets you see on site at FanDuel through data science modeling. So what does the market life cycle actually look like? How do we get from something like an idea to what you're actually seeing in our app and all the different thousands and thousands of markets we offer on a day-to-day basis? So we're working closely with our trading team, like I mentioned. Our main job is building data science models, but we're not just building models. We're working to create dashboards. We're working creating reports. We're running ad hoc queries, working with them. A lot of what our team's doing is more on the long-term scale. The traders are more handling the day-to-day aspects of things, but there's a little bit of both in collaboration with all of that. So how does that market idea generation process actually work? So you can see here some of the things that go into it, but really at FanDuel, we're big believers that everything starts with the customer. So really anything that we think our customers might be interested in, whether it's an idea we had, whether it's something our customers come to us and say, hey, I'd love to be able to bet on this, or I've seen this somewhere else. It could be something relating to a media narrative where we think our customers are going to be interested in that as well. There's a lot of regulatory considerations that we have to consider as well. So every state in the country, some states, as you know, allow sports betting, some states do not. But even within the ones that do allow it, there's a lot of nuances to what exactly they allow. Certain markets are allowed, certain markets are not. So that brings us to the topic of today's talk. So I guess just to let you all know, we want this all to be interactive with you all. It's a workshop, so it's going to be less of me talking at you and more asking you questions, getting you all involved. So I guess starting off, show of hands, who's seen one of these before at a Super Bowl party or somewhere else? So, as I mentioned earlier, like we said, we want to build markets that customers will be able to relate to. So, I guess another question for you all, who's done one of these competitions before, filled out a box, and known immediately once they saw the numbers that they had no chance, they were totally screwed? So, our goal, I guess backing up for a second, for the people who aren't familiar with this, the way Super Bowl squares work is you buy one or more of these boxes. Once the boxes are filled in, the digits 0 to 9 get filled in on the sides, and whatever you end up with, you're stuck with. That's your box. So you can end up with some good numbers, or you can end up with some bad numbers. So I guess we're going to get more into the weeds, but if anyone had to guess, what is overall the worst combination of numbers you can end up with in Super Bowl squares? What was that? 2 and 5, good guess. Any others? 2 and 2. Any others? 5 and 8. 5 and 5. All good guesses. 2 and 2 is actually the correct guess. On the flip side of things, if people had to guess, what are the best two numbers you can end up with in Super Bowl squares? 0 and 0, 0 and 7, 7 and 1, 7 and 7. Again, all good guesses. 0 and 0 is the best one, but to all this, there's nuances. It depends. So the traditional Super Bowl squares, you get paid out for each of the 4 quarters. But at FanDuel, we like to try and make it more interesting. We offer a lot of different versions. So we'll offer markets on the final score of the game, any quarter, more similar to what you do get in the game. You can bet on the first quarter, the first half, and rather the traditional Super Bowl squares experience where you get a number, you're stuck with it no matter what. If you're more of a person looking for long shots, you can bet on a long shot combo that you think is likely to happen. If you want to give yourself a better chance of a winner, you can bet those as well, but you're not going to get quite the same payout. So today we're going to walk through how it is we actually go about setting the odds for all these different markets. So building a model. First thing you always have to ask yourself is, what is our target variable? Any guesses on what would be a good target variable for a problem like this? Probability score ends in a set of two numbers. Very good answer. Any others? Score distributions. That's another great answer. A lot of what we do at FanDuel actually relates to distributions of outcomes. It's, I think, one of the things that makes our industry very unique, in that a lot of sports analytics is dealing with mean projections and whatnot. In the betting industry, we're a lot less interested in means and more about distributions of outcomes, medians, and things like that. So love to hear that answer. Distribution of bets. Yep. The last digit. Score difference. All great answers. And I think the answer to this one is there's a lot of different ways we can go about this modeling problem. First off the top, like we talked about, we're offering a bunch of different versions of this market. So we need to ask ourselves, which one do we want to offer? Is it first quarter? Is it the end of the game? Is it any quarter? And that's going to play into our target variable. And then we also have to ask ourselves, then, what is the outcome we're trying to model? So this is a binary classification problem that we're trying to offer. So if we're saying, look at this one square, 7 and 4, one highlighted, where you want to know yes or no, did the game, if we're doing the any quarter version, which we're going to focus on today, did any quarter have the score for one team end in 7 and the other team end in 4? That will be our positive case, and the negative case is either of those is not met. There's a lot of other things like forms of modeling like we've talked about where we're more interested in mean predictions and whatnot. Here we want binary classification. We want predictions between 0 and 1, and we'll get a probability on the 0 to 1 range. But what's interesting about our use case of binary classification, a lot of domains are more interested in the yes or the no. So like if you're in, say, a healthcare industry and you're trying to figure out should a patient get this treatment or not, you'll go through the binary classification modeling process, and then you're going to have to distill what might be some probability into a yes or a no. Do they get this treatment or do they not? And as such, when you're thinking about the accuracy metrics to evaluate your model, things like precision, recall, false positive rates are all going to be super important. In the betting sphere, that's less important for us. What we're trying to figure out is just simply what should the odds be? What is the probability? How do we turn that into the odds you see on site with a little bit of VIG added? But the important thing to note is there is no single line of delineation for us. When we're looking at a model prediction, if you get 51 versus 49, that's not going to really be any different than 61 versus 59. It's just going to move the odds slightly, and then from there, the customers are the one telling us yes or no, this won't happen or will happen with their bets. So as such, what we're mostly concerned about accuracy metric-wise is things like calibration, log loss that tell us kind of how well calibrate our probabilities. If we say something is 70% likely to happen and we have 100 observations that are similar to that one, are about 70 of those 100 going to have it happen? So what types of models might we use for a problem like this? A lot of different modeling techniques. Anyone have ideas for what they think might be a good option for Super Bowl squares? Say that again? Empirical? Great answer. Historical football scores will definitely play in. Was it? Logistic regression, that is a great option that we use a lot of. Any others? Say that again? Monte Carlo simulation, another great answer that we use a ton of in the betting industry, one of the most powerful tools for sure. Any others? Cool. I guess before we get into actual types of models, I think it's important to discuss how we're going to frame the problem. So for a market like Super Bowl squares, there's kind of two high-level approaches we can take to this modeling problem. First off, we can go both teams together. We'll have 100 outcomes, so each square will be one outcome, and each one will be a separate problem. So yes, no, is this 7-4 square going to happen in this game? And even if we take that approach, when we're setting up the modeling problem, we have to figure out how to frame it. Is it from the perspective of the home team? Is it from the perspective of the away team? Do we instead frame it from the perspective of the favorite or the underdog? Or we can actually go and mirror the data set and make it agnostic to those two things. And then a lot of similar considerations if we go the other approach, model each team separately. Instead of having now 100 separate models we're trying to build 10 different outcomes per team. But even once we decide to go down that route, it could be one model for those 10 outcomes we use for both teams, or we could do two separate models again, home away perspective, favorite underdog perspective, or try and make it agnostic to those things. But the big thing you need to consider if you're going with this approach is correlation, and that's a huge piece of everything we touch in the betting industry. We're always having to consider correlation and protect ourselves from allowing customers to bet on correlated outcomes, or even better than stopping customers from betting on correlated outcomes is how do we price in that correlation. It's a big driver of our same game parlay product if you've seen that on FanDuel. So a lot of these models mentioned here are similar to the ones you all threw out there earlier. So empirical, as mentioned, if you just look at historical hit rates of how often has this square happened, that's going to probably give you a pretty good starting point for a problem like this. So that's definitely a very good option. Under the umbrella of machine learning classification, we have the simplest form, which is logistic regression, one of the most powerful tools, and actually what we'll focus on today. You have things like random forests, you have XGBoost, neural networks, you can go on with the options in that realm. And then we have simulations, which are one of the most powerful tools in the betting world and generally what we use to power most of our sportsbook offering. We're not going to go as in-depth on that today, but it is certainly a very powerful tool in the sports betting space. So when we're thinking about trade-offs between a few of these big types of models, starting off with accuracy-wise, like I mentioned earlier, simulations tend to be the most accurate for a lot of the problems we like to offer in our space. They're usually going to be the best there. XGBoost models also give pretty good accuracy, but for a problem like this, I think logistic regression would not be too far behind. In terms of model explainability, which is, I think, a huge part of the modeling process in the betting world, I think we like to say at FanDuel that you're only as good as your worst line. When you're a bookmaker, like a customer can say, okay, I just want to focus on this one thing, find one thing to bet on, and all the rest of your predictions don't matter. When you're in the bookmaking world, if you make one mistake, customers will find it and you'll lose a lot of money. So having explainable models that you can sort of know when something is off is super important. That's why logistic regression is super powerful. Simulations are also generally pretty good in that sense, whereas XGBoost and other more black box models are a bit tougher in that sense. In terms of ease to build, both logistic regressions and XGBoost models have their trade-offs. So I think for a problem like this, where we have 100 different outcomes we're trying to go after, XGBoost has a big advantage in the fact that you can throw a bunch of features at it and not do a whole lot of feature engineering, which Keith will hit on a bit more in a bit. But you can just throw it all at the model, let it figure it out, and basically do the same thing for all 100 of those, and it will do a pretty good job figuring out what matters and what doesn't. Logistic regression, you don't have to spend as much time tuning parameters as you would in XGBoost, but if you want to do it right for a problem like this, you're going to have to go through the feature engineering process and all the other things we'll cover the rest of this talk in a lot greater detail, so it will take time for a problem like this. And then simulation models, depending on how in-depth your simulation goes, there's different ways to build simulations. You could do it on the play-by-play level. You could do it on the drive-by-drive level. You could do it quarter-by-quarter, but it's probably going to be a bit more involved of a modeling process and actually involve a bunch of models within your simulation. Runtime-wise, logistic regressions tend to be pretty quick, easy to build, and very good for a lot of our use cases, especially when it comes to live betting. Model latency is a huge consideration we have to think about, so logistic regressions are good there. XGBoosts are a little bit slower to run, but generally pretty fast if you're only running them once, whereas simulation models where we're running 10,000, 20,000 more simulations, they will take more time to run if you're not careful, so it's very important to make sure that the runtime is acceptable when you're building a simulation model. And then maintainability, logistic regressions, I'd say, are the easiest. XGBoost behind that, and then, like I mentioned, simulation models are tough in that they're often a bunch of submodels all connected together. So if you make changes to one, you often have to make changes to others as well and keep it all in sync. So like I mentioned earlier in today's talk, we're going to focus mostly on logistic regression, how we would go about building that out for a problem like this. So I'll kick it over to Keith, who's going to walk through some of the feature engineering process.
Cool. Thanks, Jason. I'm Keith Goldner. I also work at FanDuel. One of the things that you've probably noticed so far is that up to this point, it's all been brainstorming. We haven't put any pen to paper. We haven't written any code. It's all trying to frame the problem itself. And so one of the things that gets glossed over a lot is actually how it's going to be delivered. You can build the most accurate model in the world, but if you're not delivering it properly to your stakeholder, it doesn't get used. So really early in the process, we like to think about what that delivery looks like. Our main customer in our case is the traders that are at FanDuel. And so there's two main ways that we deliver it to them. The first is kind of the automated solution. So you've got a live feed that comes in and sits in either a database or a queue. The model runs on top of it. It goes to the server, and a trader is just kind of watching it, monitoring it. They can nudge it and adjust it in different directions. The second, we could build a model, deliver it via a dashboard. It could be an Excel spreadsheet. The trader can play around with it and then kind of manually put it up on site as they want. Optimal case is the first one. It takes a lot more engineering involved, but either way, this is something we want to be thinking about from the very beginning of building the model process. For us, we want it to be live Super Bowl squares, which you can't really do if you're running this manually on the side, so we want the more automated process. Okay, gonna ask another one to the group. Again, we're still brainstorming here. We need to start thinking about the features that we're gonna include. So we talked about what the target's gonna be and what types of models. So we're trying to figure out how many points a team is gonna score. We wanna know what has the biggest impact on how many points a team scores. So I'm gonna open this up. We're trying to answer this question. What are the features that we might include in the model? Anybody have any ideas? Weather. What else? Time of possession. What else? Point spread and the over-under. Total yards. Okay, good. These are all great answers. This is a non-exhaustive, imperfect list, but the offensive efficiency, the opponent's defensive efficiency, we said weather, how quickly the team's play is going to impact the number of points, how quickly the opponent plays. Your team's defensive efficiency is going to have an influence on how many points your team scores. Injuries, coach aggressiveness, if teams are going for it a lot more on fourth down, that's going to make a big difference in the number of points scored. We've talked about a lot of things kind of in general now, but we actually need to quantify these features. So we need them in our data set as columns that we can then run our code on to build the models. So as we're thinking about this, we have to think about what stats represent those things like weather and offensive efficiency as we're putting them into the model. And we want to have the most accurate representation. A lot of these stats can be biased. So we're gonna go through another thought exercise, more brainstorming here. We want to quantify offensive efficiency, okay? How would you think about with an actual statistic that you're going to put in a column in your CSV or multiple columns, how would you quantify offensive efficiency? Anybody have any ideas? Yards per play. Points per game, points per drive. Any others? No more? Say it again. Average time of possession. Okay, all good answers. The exact answers I was looking for. Okay, so these are all good ways that you could quantify it, but they're all going to be biased in some way. So most of the ones around points per game and time of possession is going to be heavily biased by your schedule. If you played a much tougher schedule, those are going to be very different numbers, and we want the true representation of how good these teams are offensively. Yards per attempt, not all yards are created equal. If you get 2 yards on 3rd and 10, that is not the same as getting 2 yards on 3rd and 1. The defense is willing to give up those yards on 3rd and 10. They're not on 3rd and 1. So stuff like expected points added or expected points added per play that adjust for that sort of thing is going to be a better, less biased metric. So here's the list of features that we kind of talked about. We're actually going to simplify this a ton. We're going to go back and look at kind of the spread and total, which we know are efficient from the market. And we're going to use implied team total, which basically takes the spread and the total, and it approximates how many points are expected to be scored by each team. So here's a look at that. This is an example of feature engineering, where you take kind of 2 raw features and turn it into something else. You've got a total of 48, a spread of -4, and here we're saying that the Cowboys are expected to beat the Commanders 26-22. So that's going to be a good indicator that includes all those things like offensive efficiency and weather and injuries and coach aggressiveness that we can then put as a more simplified feature into our model. Okay, now we're finally going to put some pen to paper here. There's the old adage, garbage in, garbage out. If you do not have good data, your model is not going to be good. So the things that you have to do with data are collect it, organize it, clean it, and then engineer features. So I'm going to talk through that briefly. If you've seen some of our workshops before, this might be repetitive, but it's very important because if you, again, don't have good data, you don't have a good model. So where do you collect data? Usually via an API, hopefully an existing database that you have, through web scraping. A lot of different avenues for doing this, but you need to have good data from somewhere. You want to immediately be thinking about what format do I need this data in. So in most cases, this is like tabular or CSV data, where you have each column is a potential predictor that you're going to try in the model, and then you have a target column as well. In our case, that's going to be whether the target was hit for 7-0 in that observation. So each row is an observation. We have the team implied total, the opponent implied total, and that's what we want our data to ultimately look like. So as we're gathering and cleaning, we're putting it in this format. Okay, here's kind of the things you need to think about when you're verifying and cleaning your data. I'm going to go through each of these pretty quickly, but removing duplicates, clerical errors, missing data, outliers, and then you always want to sanity check everything you do. So duplicates, here's a couple of examples. This is our NFL player database. You can see there's 5 Brandon Williams. You always need to be using player IDs and team IDs and game IDs so that you're not attributing the wrong statistics to the wrong player when you're trying to build a model. And then here's another one where context really matters. If you kind of just looked at this first thing, you might think it's a duplicate observation, but when you add in the contextual data, it was actually 2 different games, and we would want to include all of that in our data set. Clerical errors, data errors, again, here's just some made-up examples. In the first one, we have an implied total of 10.5. That's not impossible, but that's extremely low for a game, so we'd want to go check and make sure that was right and not some sort of error. We have a string for yes instead of 1-0. We'd want to keep that data point, but just convert it to something that's actually going to be read properly. And then the target in the last one of -1, you can't have that. It should be binary 1-0. So we got to go look, is that a clerical error? Is there something wrong? Do we have to throw it out, or can we actually use that observation in our data set? Similarly, very similar is basically null values or missing values. We don't want to just throw out data. If we have good data, we want to make sure there's no systemic issues with our data, so you want to go back and look. Not having an implied total, we can't really use that. If we can't fill it in, we'll throw it out. You see that playoffs is null for these two. Maybe that's just how it was recorded in our left join or something like that, and we can actually put in zeros for there, and it's very usable. And then if you use Excel, you're probably familiar with the NA, and again, we'd want to see if that's usable or if we need to toss it out. Checking outliers in everything in sports modeling. Histograms are your friend. You should be using them early to look at the distributions here. This is just looking at the score distribution in 2022. We have a data point that's under 0. That obviously can't happen. We have one up by 80. That can't happen. We'd want to go look, again, is there an issue with our data source? Figure out if we need to go back to the drawing board or if we can actually use this data. And then last, I mentioned this before, but sanity checking. Does it make sense? So this is looking at implied totals versus the actual score. We would expect it to be predictive if betting markets are predictive. On the left, you see it goes up as you would expect. On the right, it kind of acts funny about halfway through. If you saw that, you'd think, hey, maybe there's something wrong with my data here and need to go back to the drawing board. So never live entirely through your data. You want to make sure everything makes sense, sanity check, be humble as you're creating these models. And I mentioned feature engineering. Again, the the implied team total is just a good example of engineering a feature where if you think you can build a more predictive feature from existing raw information, it can be really valuable as you're building those models. Okay, I'm going to pass it back off after my middle relief appearance.
Perfect. Thanks, Keith. So getting into a bit of the modeling process. So once we've gone through all those checks that Keith mentioned, one of the big things I hit on earlier we have to consider is correlation. So you can see here I've put together this little table of scores. You can see, like I mentioned earlier, 2-2's the least common occurrence we've had in our database of games. 0-0's the most common one. But that's not really telling us much of anything about the correlation here. There's not a whole lot we can tease out yet. If we ran your traditional correlation command in R, that also wouldn't really tell us a whole lot in this context, because 7 versus 8 is really no different than 7 versus 1. Like, it's either yes or no. It's not like we're working on a line where those two are closer to each other. So we need some other way of trying to figure out what's the correlation between one team's score and another team's score. So instead, if we do a bit more wrangling with our data, we can get to this look where you can see here, basically the way to read this is that, okay, go to the number on the left, which is a 4. If your team's score ends with 4, then there's a 3.7% chance that the other team's score ends with 8 in that quarter. So now when we're trying to look at the correlation here, we might look more at these two observations highlighted, where given that your team's score ends in 0, there's only a 4% chance the other team's score ends in 1, versus if you have your team's score end in 8, there's a lot more, almost triple the chance that the other team's score ends in 1. So can anyone guess, using your football instincts, why this might be a thing? Do we think it's just a small data thing, or do we think there's something to this effect? Going for 2 to get down 3. Any other ideas? Field goal after a tie game. Yep. Yeah, I think that's the big one right there in my mind, is that when you're considering the ones tend to happen later in the games, like the 21s, your 31s, and whatnot. So it probably isn't happening as much in the first quarter. Similar with the 8s, so that's why your 1s and 8s tend to be more correlated with each other, whereas 0s tend to happen a lot more first quarter early in the game when the 1s don't happen, so those are going to be a lot less correlated with each other. So clearly there's some level of correlation here we think we have to control for. So I think there's 2 high-level approaches we like to use for handling something like this on this kind of problem. First one, to just take out the correlation altogether, is just directly model the outcome you're trying to figure out. So for this example, we're going to say, is any quarter end in 7-0? So we can just directly go yes or no, did any quarter end 7-0? And it will work great, pricing the correlation directly. If we're talking about another context, like a same-game parlay, and we're trying to say, okay, will Jason Tatum score 30 points and the Celtics win? We can do some correlation adjustment for Jason Tatum scoring 30 and the Celtics winning, or we could just directly model yes or no, did this player score 30 and his team win? And then I think the other high-level approach that we use a lot is conditional probability, where you can say, okay, we're going to model one thing, and then conditional on that one thing happening, what is the probability this other thing will happen based on that? And then I guess the third option I didn't mention as well is simulations, another powerful tool that we don't touch on. But for the sake of today's thing, we're going to focus on the first option, take out all the correlation considerations, and just directly model that one square we're interested in. So getting more into data wrangling, like we talked about, we offer a lot of different versions of Super Bowl squares, but for this problem, we're going to focus on the any quarter version. So we got to basically take our data set, first grab quarter by quarter results. So you can see here we've got 3 sample games. We've got for each quarter what the home team score was, what the away team score was, and yes or no, did the quarter end 7-0 first team, second team. And then we can basically distill that down from the quarter level to the game level. And I think what's really important for us to ask ourselves early in the modeling process is like, what are these corner cases? What is going to be something that might cause customer pain points down the line? So with a problem like this, you think back to your Super Bowl squares example from the beginning. Customers are used to sometimes getting paid out twice if a score hits twice in the game in different quarters, but that's not really something we do. It doesn't play nice with binary classification, logistic regression. So it's probably one that we're going to want to clarify with customers. Hey, even though it's in any quarter market, you can only win once, even if it hits in 2 different quarters. So you can see here in the second game example provided, it hit in both the third and fourth quarter, but we're still just going to treat that as a 1, just like we will in the first game, where it only hit in the first quarter. Another corner case that might pop up with customers is, what if the game goes to overtime? You're going to now have 5 different possible points to pay out. You'll have the end of the fourth quarter, you'll have overtime. The question becomes, do we pay out at the end of the fourth quarter? Do we pay out at the end of overtime? You're probably going to have customer complaints if you pay out in overtime and their score 1 at the end of the fourth quarter. They're going to complain the other way, vice versa. So we can actually get around that in a situation like this by just pricing it in, paying out both. And that way, customers might have a slightly smaller payout at the end of the day, but we're going to take out that pain point that if their score hits in either the end of regulation or in overtime, they're still a winner. Another tool I talked about a little bit earlier on that's powerful is mirroring your data set. So for a problem like this, if I go back to the slide before, you can see we had set up home team, away team, yes or no. Did the 7-0 square win from the perspective of home team the 7, away team the 0? But let's say we think we've done our feature engineering well enough that there's not necessarily a difference in basically a home team who's a favorite of 3 points versus an away team who's a favorite of 3 points. We can mirror our data set, basically end up with twice the number of observations and take out some of the noise that might have presented itself from NFL. We only get a few hundred games per year. So it helps out a lot. So you can see here, basically we've taken game 1 on the left where first quarter 7-0, just flipped it. Instead of being from the home perspective, we did it from the away perspective. We keep both of those observations as 2 separate games, and now we've doubled our data set. So like the first game switched from being a winner to now is, in the mirror data set, is not a winner. The second game hit in the third and fourth quarter from one perspective. From the other perspective, it hit in the first quarter, both winners, so it didn't change there. And then the third game didn't hit in either way of approaching it. So now we've got our data set ready to go for our actual modeling. So let's actually put together a model. We're going to focus on the 7-0 square to start, like I mentioned. So you put together a regression in R or any other. There's lots of other coding languages you can use as well. And say, okay, we're trying to predict yes or no. Did any quarter finish 7-0 as a function of our team implied total, which Keith explained to us how we got to. We have our opponent implied team total, and we also put in a season term to see if that's significant. So when we're looking at these results from our regression, first thing that pops out is we've got this positive coefficient on the team implied total telling us the better this team is, the more the 7-0 square hits. That makes sense to me. I guess backing up for a second, the 7-0 square, given our conversation earlier, where do we think within a game it's most likely to happen? Yep. First quarter. Any other guesses? Yeah, I would definitely agree first quarter is the most likely one to happen, and I think the most likely way it will hit is the score actually being 7-0. It can also hit in the case like 7-10, or anything like that, but 7-0 in the first quarter is going to be the most common case of it. So it makes sense that the better your team is, the more likely it happens, the more likely you score a first quarter touchdown. But it is a little tricky for a problem like this where we're doing Super Bowl squares for any quarter to interpret the coefficients, because it can get yourself in a little bit of a pretzel of like, okay, there's a lot of different ways for this to win. It can happen in a lot of different quarters. But for this one, it seems pretty clear. It makes sense with football intuition that the better your team is, the more this will happen. And similarly, the better your opponent is, the less this hits, or the worse your opponent is, the more it hits. Again, makes sense. More likely that they'll score nothing in the first quarter, and this will hit. And then we have this season variable we tried as well here. You can see there's a positive coefficient, and then if you look at our p-values on the right, it's right on the edge of being statistically significant, p-value around 0.12. And when I see a p-value like this, I think the big thing I tend to ask myself when I'm trying to decide yes or no, should I leave this in my regression, is does the theory match up with what this number is telling me from the model? So if anyone had to go off their football theory, do you have any theories for why this positive coefficient might be there for season on if we'll have 7-0 ending a quarter? Any guesses? Yep. More scoring generally, for sure. That's a good one, but I think the one thing you always have to keep in mind when you're thinking about your variables like this is that you have to consider correlated inputs. So in this case, our team implied total, opponent implied total should already be pricing in the aspect of higher scoring. That's not to say they always will be, but there's going to be a lot of relationship there. So I'm glad you raised that because you always want to be considering none of this is in a vacuum. It's all relative to your other features you have in your model. Yep. Rules changes, for sure. Kickoff rules, definitely. And I think related to that is increases in touchdowns, less field goals. Teams are going for it more on fourth down these days. You get more 7s in the game, less 3s, so it makes sense that you'd get more 7-0 squares accordingly. So it makes sense to me. I think we should probably leave it in our model. So then the next thing we want to ask ourselves, okay, is this model any good? What I mentioned earlier, we're interested in model calibration. So we'll build something like this, which we call a calibration plot. What we're basically doing is taking all of our data, we're going to order it from the lowest prediction all the way up to the highest prediction, and then we're basically going to cut our data into a bunch of equal size bins. So for example, you can see at the top there, our first bin, which is all of our lowest predictions. The minimum prediction was 7.9%. The highest prediction in that bin before we cut it off was 15.1%. The average prediction was 14%, so it seems like more of the observations in that bin were towards the higher side, which makes sense on the extremes. And the average actual hit rate on yes, no, did the 7-0 square hit was 15.5%. And you can see that little dot in the bottom left of our graph there, it's slightly above the diagonal. So the big thing we're looking for here with these calibration plots is are our dots basically straddling that diagonal 1-to-1 line? If it is, and there's no pattern to kind of the way they're falling above or below, we're going to be pretty happy with how our model is doing. Seems like we're in pretty good shape here, so we like that. We've got what we think is a pretty good model. So let's go on to another example. Let's do another common square, 0-0, actually the most common one we talked about, and we'll go with a similar form of model, but slightly different. We're going to add in an interaction term. So I guess first things first, one thing that jumps out to me when I'm looking at these coefficients is you look at team implied total and opponent implied total, and everything in that row is exactly the same. Does anyone have any guesses why all those numbers are exactly the same? Yep. Pick'em game, good guess, but we have actually lots of different games within our data set, so we'll have a mix of some pick'em games definitely in there. We'll have some bigger spreads. Yep.
Because of the data mirroring.
Yep, exactly. So going back to when we did the data mirroring process, for every game where one team's the first team, the team implied total, there's an identical game where the other team is that team's the opponent. It's a bit of a tough one to get your mind around, but the point here is that since it's a 0-0 square where both team scores are the same, we basically have two identical observations on each side. So from our mirrored training sets, we get these identical coefficients. But they're a bit more difficult to interpret now because we've got this interaction term in there as well where we interact the two together. The reason we put this interaction term there, going back to our theory, is that there's probably going to be some level of correlation between, like, do you have a high-scoring team, a low-scoring team, and how much this 0-0 square will hit. So when we're trying to figure out how do we actually interpret these coefficients, I think one of the easiest ways to try and wrap your head around it is use one of the simplest tools there is, Excel, and you can basically take your coefficients, take the portion of the regression that relates to those two variables you're interested in, put a reasonable range of values on the x-axis, put a reasonable range of values on the y-axis, and then set up a formula like this where you can say, okay, within my regression, what is the portion coming from these two features? So you can see here, I have added some conditional formatting in Excel to basically put colors on it so it's nice and easy to read. But what we're basically seeing is, okay, these interaction terms, these coefficients are telling us that 0-0 in a quarter is most likely to happen when you have two low-scoring teams. That makes sense. 0-0, as we can all probably guess, is most likely to happen early in the game in the first quarter with low-scoring teams. So it makes sense that it would happen the most in games like that. On the flip side, you can see in the top right or bottom left, it's least likely to hit in games with one high-scoring team and one low-scoring team. Again, makes sense. You're going to have basically that one team probably scoring a lot of touchdowns, so you're losing the chance of having it hit later in the game. So if that team's just going 7, 14, 21, they're never going to end up back on a 0, versus if they're more mixing field goals, you might land on a 10, you might land on a 20, whatnot, or you also have the 0-0 case in the first quarter. So all that makes sense to me that one high-scoring team and one low-scoring team would mean that we're not going to have a lot. And then just slightly more likely is if you have two high-scoring teams, and it makes a bit of sense to me that that would be more likely than the high-low case, because you're going to have the teams closer together. You're not going to probably have as much motivation for teams to go for two. So as such, you'll probably stay on more even numbers. You'll have your 7s and 3s and maybe a better chance of landing on 0s. So we've got our interpretation of our interaction terms, nice, easy way in Excel. And then one last example we've got for you guys if we're trying to do the 4-3 square. This is a good example of a spot where you can see we've added a square term to our regression. Second order and higher polynomials are often very useful when you have nonlinear effects. And if you're trying to, you can see here it's clearly statistically significant, but if you're wondering how do I figure out in the first place that I actually needed it, there are nice easy tools like ggplot where you can plot the effect of a certain feature on your dependent variable. You see how we get this nice plot with the curve thing. That makes sense to me that we're going to want a second order term as compared to if we just had a straight line on the graph, then we're probably fine sticking with our linear predictor. So once we've actually gone through the full modeling process, built all these models, super important to actually test your model. So the goal is always try and break what you've built. Think about corner cases. So usually you want to try and build in some level of automation to this process, but starting out you want to hit your normal inputs, make sure everything passes the sniff test. Obviously your subject matter expertise is going to matter a lot for kind of doing that sniff test and knowing that, this seems off. You can also pull in your domain experts, so in our case, like the traders, send them some sample predictions, get their thoughts, see if it makes sense to them. Then next thing you want to do is try bad inputs, put in some values that are impossible, see what happens, really trying to push the extremes of your model, make sure it handles that well. You're going to want to, if you're actually automating it, consider like possible issues like bad data types. So maybe if you're scraping and you might scrape it as a string instead of an integer, you want to make sure something like that does not break your model. And then, like I mentioned earlier, you always want to consider any sort of edge cases and make sure you're happy with how your model's handling those, because that's often where our sharp customers are going to try and find ways to beat us. And then, like I said, the biggest thing we want to do is actually make sure it gets to production, it gets used. I think it's important for a context like ours. I think anyone who's looked at our app knows we have thousands and thousands of markets on site, and it's easy for a market to get lost. If we have one that we think is relevant, we want to surface it in a way that it's easy for customers to digest and figure out what's going on. So if we went back to the beginning, you know everyone's used to the Super Bowl square sheet. As much as we can work with something like our design team, our product team, to build a nice UI to surface all this in a clean, easy to navigate manner for our customers, the more our customers are going to bet it. And then the biggest thing after that, once we've got our model in production, it's not over. We always want to be iterating. So once we've got deployed, once we've got tested, it's in front of customers, we're going to get a lot of feedback in the form of bets. So we're working with our trading teams, our risk teams to take that bet information and then continue to see, oh, maybe this customer picked up on something we forgot about. Do we need to go back to the drawing board, adjust our model a little bit? It's very easy in the betting space to get a lot of feedback on if you have a good or bad model. You just look at your profit or loss. If you're making money, you've probably done something right. If you're losing money, there's probably something that's gone wrong. So there's always going to be some level of variance, so we don't want to overreact to results, but it is nice in that we get a lot of real-time feedback from customers. So that is everything we had. Any questions about anything we've covered? Yep.
You mentioned that I think you said throw out the offensive features in favor of the implied score. Why not just leave all those in and see what shows up as significant?
It's a really good question. So I think number one, it depends on what kind of model we're using, whether we're going to leave it in. So say we're using something more advanced like an XGBoost model, then you're going to be more prone to overfitting if you have a lot of correlated features in there or things that aren't necessarily significant. You're going to have some similar issues with logistic regression, just to a smaller extent. But in the NFL, where you really don't have huge data sets to work with, overfitting is a huge problem. So that's a big part of it. Data pipelines, the more you need to set up, it's going to make your life harder. So if you can distill it down more, that's awesome. I'd say those are the main ones. But yeah, good question. Yep.
Can you go back to your last slide?
Yep.
So, according to these slides, the data scientists come up to the end of the process of deploying the model to production and making it as efficient as you need it.
Say that one more time.
Are data scientists, according to this, in charge of taking the model to production in your company?
Yeah, so the way we do things most of the time, we're working with a team of engineers to productionize our models and make them run fast, especially if we're going to be using that model live. Like we mentioned, latency is key in our context with live betting, so a lot of times we'll take our models, work with engineers to put them into a language like C# and make them run faster. But we also have some other use cases where we're sending directly on site, where we're sending across dashboards to traders, and they're going to take it, look at the predictions, post them. So there's a lot of different options, but for the cases where latency is most important, we're often going to work with a team of engineers to work together to make it run fast.
What is like a typical latency?
So it depends obviously on the use case, but when we're dealing with live betting, we like to try and keep things over 1 or 2 seconds. Anyone who's bet live themselves has probably encountered what we call a live betting delay, where basically once you click submit on a bet that's live, you might get like a spinning wheel for a few seconds, where basically we're protecting ourselves from the latency of the bet, making sure you're not at the game typing in faster than our models can update. So really it's about tying those back together and making sure that customers are having as close to a frictionless experience as possible, but we're also protecting ourselves.
So under what circumstances will you realize your model needs to be readjusted and it's not just like purely unlucky?
Yep. So I guess a few different ways we can go about that. One is we can see over a large enough sample that if you're losing at some point, the noise is going to fall out. So if we have a full season of losing, that's probably going to tell us something's wrong. Another thing I think we can do is look at customers who has historically proven to be pretty smart. If we see, okay, this customer always wins and they're betting against our model, that's probably a pretty good sign that we want to look back and see, did we miss anything? Yep.
Kind of going back to what you were talking about earlier with overfitting, how do you sort of balance the concerns about using historical data, kind of going back multiple years because that's not going to be as representative of today's sport. How do you balance sort of that concern against trying to increase your sample size to prevent that overfitting concern?
Yep, that's definitely one of the toughest challenges we have to face is like you always want the most recent data, but you also want enough of a sample size. So one example we gave, you can put a season variable in your model, and if you think it's like a trend's dependent on another feature, you can interact that season feature with something else, or just put season in on its own. There's some other methods, like you can upweight more recent data within your model to try and put more emphasis on recent data without losing the older data points. So I think both of those are good options.
When you see a certain square, maybe a group of squares being overbet relative to the price it is, what's FanDuel's process for changing the line of that square? And
Yep.
how quick does it happen?
So that's a great question. Not just Super Bowl squares, but really any market. There's, I think, a common perception that Vegas and sportsbooks just want to balance the book, which isn't really the case. Like, obviously, we're going to consider the bets like I talked about. That's feedback for our model, and we're always going to consider that. But if we see these bets, we feel good that people are just betting it because it's a fun bet or whatever it is. We think our model is good. We've looked back, double-checked it, all of that. We're going to not necessarily change the odds just because we're trying to balance our book or something like that.
So are you guys, like, follow-up question, are you guys more concerned about finding the true probability that you believe that event will happen, or balancing the books of what the public and sharps bet?
No, it's all about trying to find the true probability of things to happen, for sure.
How much weight do you put on the interpretability versus just performance? Like, if your calibration's spot on, do you really care about the p-values?
Yeah, I'd say obviously accuracy is super important, but we have found in our experience that models that aren't interpretable in most use cases are going to have holes that customers are going to find. So accuracy metrics are obviously a great tool. We talked about some of the ones we find more interesting, but they don't always tell the full story in the betting landscape. So, like, take, for example, you had two models. One of them was always off by 1% on every prediction versus another model that 99% of the time was perfectly spot on, but 1% of the time was miles off. We're always going to take the one that's 1% off all the time because we have the VIG to protect us, whereas if we make that one mistake, that will undo all the good we've done on the other 99% because customers will find it, it doesn't pass the sniff test, and we'll lose money.
How do you, for example, in this square, assign the margin of the odds? And does this margin depend on the already placed bets?
Yeah, so our team specifically is not as involved in the process of adding the margin. That's more our trading and risk teams who focus on that for the most part. But really, when we're considering the margin on the market, I think, number one, we try and be super fair to customers. Like, we're not trying to make as much money as we possibly can and, like, make it criminal. Like, we want to be fair to customers, provide a good experience where they can come to FanDuel and get the best payouts compared to any other book. And then really what it comes down to is, like, confidence in the pricing. We need to protect ourselves and make money, but we want to be as fair as possible.
Thank you.
For the squares in particular, are there any of the numbers like 2 or 9 that really have no features that are really correlated to it? You know, to get to 2, probably a safety in the first quarter might be most likely. And for those, do you just say, okay, the probability is X and let it run?
Yeah, it's a good question. If you were to basically go about pricing up all 100 of the squares the way we outlined here, there would definitely be some where it's just pure noise.